The objective of today's lecture is to go over forward kinematics, the first lecture on forward kinematics. What's the objective? Exactly is to determine the position of the tip of a robot given the orientation of all angles and all prismatic joints and the displacement of all prismatic joints. So today we're going to see a method to do that that works for any type of robot. Instead of actually going with a geometric or trigonometric approach, we generalize the concept using the frame transformations that we saw in lectures 2 and 3 and see how we can apply them to describe the position in space of any joint of a robot manipulator, of any movable parts, especially the tip of the or the end effector of the robot in terms of orientation and position. So today we're going to look at a planar kinematics, that means 2D, two-dimensional on a plane. And then in the next lecture, we're going to simulate this in Matlab, and then in lecture 5, we'll expand this to a spatial kinematics, that means in 3D. So we'll start here, and then we'll complicate these things a little bit later. Now, this is not an easy topic, I have to say up front, and to be honest, I don't expect you to fully grasp all the contents you'll see today. It will take some time to sink in, because there's a lot of information, there's a lot going on. But the advantage of this method is that it works for any type of manipulators. So today we're going to define the minimum set of variables that we need to orient a frame in space, establish a convention to assign frames to different movable parts of a robot arm, and then calculate the forward kinematics of planar manipulators. And by forward kinematics, again, what I mean is if we know the displacement of prismatic joints or the angular displacement of Revolute joints, where is the tip of the robot in space? Let's take an example here. We have these two surgical arms that are performing laparoscopy. A question that we can answer with what we're going to see today is if we know the position of all joints, if you know the displacement of all joints, where is the tip of the robot in space? And again, when we're talking about where, we are talking about with respect to something, with respect to a reference frame. Now, are we talking about the position of the tool with respect to this frame, that frame, or the base of the robot? Well, we can calculate all of them using the concept of forward kinematics. All we have to do here is to assign frames to different parts of the robot and then create the transformation matrices between them and then connect them in cascade to go all the way from tip to the base of the robot. That's the application what we saw in the last lecture. Here is another example of what is the position of the end effector given the angles of each joint in the robot arm. And the way you're going to do that is by assigning frames to specific joints of the robot, assign angles to each of these joints, and then using the transformation matrices we established in the last lecture, we can calculate the position of the orientation of the end frame there with respect to the base. And hence we know the position of the end effector of the robot in space. So this has been done for us. We don't need to start everything from scratch. There's a convention used in robotics. And we're going to go over that quickly. So it turns out that to orient a frame in space, we only need to define 4 transformations. 2 rotations and 2 translations in space. And by doing that, we can simply take the resulting transformation, the homogeneous transformation that each of these manipulations creates, and then multiply them to calculate the full description of a frame with respect to another frame in space, with translation and rotation. So we need a minimum of 4 successive operations in a predefined order. Now this predefined order can be the way we want. There is a convention though, so everybody speaks the same language, and that convention is what we're going to use here. But if you want to use a different convention, a different sequence of operations, that's fine too, so long as you're consistent across all joints. So the first one is a rotation about Z by theta. So we have 2 frames there, frames A and B. The dark one is the fixed frame, and the gray one is now being rotated around Z by theta. What's the homogeneous transformation now that connects these two? Oh, it's the rotation matrix and the translation of frame of the two frames concatenated. Remember that? What's the rotation matrix? Oh, it's simply the rotation matrix around Z by theta. So it's a 3 by 3 matrix. What are the components of that matrix again? The first column would be cosine theta, sine theta, minus sine theta, cosine theta. Remember that from the last lecture. Right? And then for Z we have 0, 0, 1. Yeah? Does that ring a bell? That's from the last lecture. Sure, that's what goes in here. This is basically saying that frame P is rotated about Z with respect to frame A by theta, and R is then the rotation, the 3 by 3 rotation matrix that accomplishes that transformation. But we need the full description of those frames, so we also need to consider the translation. So that's the vector that goes in here. Right? You just notice there, it's all zeros because the frames are coincident. The origins of those frames are coincident. So we have a vector of 0. So the displacement between them is 0. And what's the last row there? What's the last row? What's this one? Does that one represent?
The original.
That is just a row of zeros and one to balance the size of the matrix, right? So this is the displacement. It's the B org, the origin, and this is the rotation. So that's the first manipulation I'm going to do. We're going to simply rotate one frame with respect to another by around Z by theta. The second is the translation across zeta. So you rotate about zeta first. Now you're going to translate about zeta, Z, by the amount D. So we rotate about Z. Now translate about across Z by D. What's the transformation matrix? So it's again a rotation matrix. Here it is. What's this rotation matrix saying? When you have an identity matrix there, that there is no rotation between the frames because the component of XA and XB is 1 and 0 everywhere else. So X's are aligned, so are Y, so are Z. Does that make sense? All right, so we have an identity matrix indicating that the axes are aligned, but they are shifted in space across Z by amount D. So that a B origin vector now has three components still, 0 in X, 0 in Y, and D across Z, because you're simply shifting that up across Z. Does that make sense? Yeah? So far so good? So that is the second operation. Any questions? Yeah?
So here we have the situation that during the shift from that. So how about the other two? If we have like the shift from X or Y, where the E should be?
If we had a translation across Y, then D would be here. Right? If it was across the X, so the frames are on this plane here and one moves forward, then it will be D there. But we are limiting this translation to across Z by definition, right? By the convention. Now the next one is also a translation. And look, this will answer your question better. It's also a translation, but it's a translation now along X. So the two frames are on the plane here and taking one frame out. So I'm sliding it along X by a amount A. So you see the transformation matrix is exactly the same as before. The identity matrix for the rotation matrix indicating that the frames are aligned, but they are now shifted along this X by a amount of A. So now you see here how the vector changes. That answers your question. The translation now occurs across Z, across X. Does that make sense? And then the last transformation is now a rotation across X by the amount alpha. So what happens? We have a rotation matrix across about X. Rotation matrix we defined in the last lecture. What would be the rotation matrix here? For the first column along X would be 1, 0, 0, second column would be 0. Then it would be negative cosine, sine, and cosine. Right? That's the translation across the rotation across x from the last lecture. And then we see here that there is no translation between them because the shift translation is simply 0. So simply a rotation around x. Now you have these 4 operations, and these 4 operations are sufficient to now fully describe, fully position a frame with respect to another. We're going to do these operations in the order that is presented here, but as I said, different textbooks, for example, in robotics, we use different conventions, so some of them may change the order here, but this is by far the most common one. So we do a translation across, a rotation across z, then translation across z, then rotation across x, and then rotation across x. So here is the 4 operations multiplied. That's the advantage of these transformations. We can now simply multiply them to perform all these operations in a given order. And with these 4 transformations, now we can fully position frame B with respect to frame A. And the result of that manipulation is this nice matrix here. So we have now theta alpha at the rotation angles, G, the translation across Z, and what else we have? A, the shift translation across X. So if you want to now find the entire transformation matrix, all we need to know is the translations and the rotations, and then plug the values here and define the transformation that way. The good thing about this is that we now have a convention that works for all joints in a robot arm, so long as we are able to now properly position these joints in different points, strategic points in space. Yeah?
Here is the order important.
The order is important. If you flip the order, then this equation flips.
Here we started with the rotation of alpha. Right?
We start, yes, so we are rotating of current frames. Right, so we start from the last and we multiply back. So if you reverse this, it still works. All we have to do, just have to make sure that we are consistent with these rotations. So that's now the transformation from one frame to another. So, yeah.
Again, so in this scenario, we just rotated alpha and then have a shift of A and shift of B and then rotation again this theta.
Yeah.
Okay.
Yeah. So 2 rotations, 1 translation. All right. So now that I know how to find these, fully describe a frame in space with respect to another with these 4 variables, we need to strategically place these frames in certain points of the robot, and then go from there. So let's assume here a very simple robotic system. We have 2 links, 2 movable parts of the robot. They are connected by 2 axes here. They have link I and link I minus 1. Right, so to define a frame with respect to another frame, we simply need now to find theta, d, alpha, and ai. So how does it work? Here we have 2 links. So this first one here is link 1. It's called this link 1. And this is link 2. We have 2 axes here, so let's call this axis A1, and this axis here will be A2. Now we need to properly position the frames. Where would be a good point to place these frames? What's the objective again? The objective is to determine the position of certain parts of the robot in space. So where would be a good point to place these frames? On the joint or at the end of every link, because that's eventually what you want to know. So it would make sense to place the frame that describes link 2 at the tip of link 2. The frame that describes link 1 at the tip of link 1. So we'll place a frame for link I at the end of link I. So we know where its tip is in space, and then we know where the next one will be in space later. So frame I goes at the end of link I. That's step 1. Next step is, that's step 1. Next step is to place the z-axis. And you're always going to place the z-axis along the rotation axis of each of those frames. So notice here that we're placing the frame at the tip there. Right? So this is axis 2, describing link 2. This is axis 1 for link 1. So Zi will be placed on axis I plus 1, which means that if here we have axis 2, this is Z1. Right, so Z is 1 behind the axis. What is this Z1? Well, this Z1 is, the idea of Z1 is to give the position of link 1. So it goes at the tip of link 1 along the actuation axis. So if that is Z1, then this one here should be Z0. And the next one there, we could place a axis here, axis 3. This would be Z2. Right, so Z2, this frame here you are constructing to describe link 2. What's the next step? The next step, so this is step 2, place the Z axis along the actuation axis. The next one now is place XI. So XI goes with ZI. And you're going to place XI, now read this carefully, along the common normal between Z minus 1 and Z. And ZI. So let's say we want to place this X1 here. We want to place X1 in a way that X1 is normal to Z0 and Z1 concurrently. It has to be normal to both axes. What's the only solution there?
90 degrees between both of them.
Oh, sorry, it goes call normal, not perpendicular.
Oh.
Right, so it has to be on the plane that is formed by Z0 and Z1. So the only solution is to place it like that. It will align with link 1. It is on the plane formed by these two axes, so it crosses Z1 and crosses Z0 at a 90-degree angle. This is just to say that by doing that, Z1 will be along link 1. Z2, X2 will be along link 2, and so on. All right, so X1, is here. That is X1. I'll let you find X2. Where is X2? Is along link 2. Right, so we have a plane created by these two here. X2 goes on that plane, so it needs to be facing that way. Well, it could be facing this way, but here's another rule. Xi points towards the next link. Right, so that we know the plane where it should be the direction. Now the direction is given by pointing towards the next link. So Zx3 would be, X2 would be going like that. So that's step 3. 3, place xi. The last operation, yeah.
So we don't make an x0 in this.
Oh, we can make an x0. Yeah, we can make an x0, but the problem with x0
You don't have
is that we don't have x minus 1. So where does x1 go? That's arbitrary. That's up to us to define. It's better to just keep the same direction of x, the next x. So I would put it pointing that way and put y pointing up. And then the last one is the direction of y. And the direction of y, we can't choose it. It's simply determined by the cross product of z and x. So let's take the middle one, x1. X goes z, so x goes, z goes to the front. x1 goes that way, so y goes up. y1 goes up. Well, at a 90-degree angle with x1, right? So let's do this properly. Y1. So x goes that way, z is coming out of the screen, and then y goes up on an angle. Where does y2 go? So z coming out, then x also goes up. Right? So goes up. So something like this. And then for Z0, the very first one, which will serve as our reference frame, we can place it the way you want, but we can place it to make it things simple, just in the same direction, like that. Now everything that we express will be with respect to this fixed reference frame. How many transformations do we need to go from the tip of the robot to the back of the robot now? We need 2 transformations, one from link 2, from frame 2 to frame 1, and then one from frame 1 to frame 0. Each of those transformations is made up of 4 basic operations, those 4 basic operations that we saw earlier. Okay? This robot rotates. Where are those rotation angles? How many rotation angles do we have here? 2. 2. Right? One is here, and one is there. Which angle is this? Is this angle controlling which frame?
It controls frame 0, 1, and 2.
Well, directly controls frame 1. Because I will rotate this by a certain amount. You see there is now a rotation about Z by a certain angle. So there we have the first variable. So this would be theta 1.
As it goes out of the page.
As that's coming out of the page. Okay, so it's rotating that way. This angle basically dictates the orientation of that frame with respect to this frame around Z. And same goes for the other frame there. This is theta 2. So notice here that we start to get into a pattern. The pattern is for axis 1, we have frame 0. But we have the variable controlling frame 1 behind. For frame 2, for frame axis 2, we have frame 1, and then we have the angle controlling frame 2. Again, 1 behind. And then for frame 2, axis 3, we have frame 2, and if we had another link, then we would have theta 3. Does that make sense so far? Yeah? Okay? Yeah? Questions?
Where is the
Zeta?
theta C?
Theta
So
3.
it is the Fano angle in that.
If to have a theta 3, we would need another link here.
Okay.
And then this would be theta 3. Right now we don't have it, so we only have two angles, and this we can consider to be the tip of the robot. Yeah.
Could you explain how you Is that pointing up, is that pointing out of the page, or is it up?
So y is given by the cross product of z and x. So if you take the first one here, z is coming out of the plane, x is going that way, so the cross product is up. So y goes up. Any other questions? No?
Sorry, I have one now.
Yeah.
So here, this data, it is always be counterclockwise or it could be clockwise?
Good question. So theta can be both ways, and you're going to assume, as in physics, that any displacement counterclockwise is positive, and anything clockwise is negative. All right, so here we have the frames we assigned before. Now let's try to describe one frame with respect to another. So the second frame here, we call that frame. Let's give these numbers because otherwise it becomes too complicated. So this is frame 2, 2, 2, and this would be frame 1, 1, theta, theta 2, theta 2. Okay. Okay, so we lost one. Let's see how many will survive until the end there. Okay, so now we can get the position of frame 2 with respect to frame 1 by specifying how much x2 was rotated with respect to x1 about theta 2, or by theta 2. About z1 by, let me start that one over. We can describe the position or the position of frame 2 with respect to frame 1 by first finding theta. And theta is how much theta x2 was rotated with respect to x1 about z1. And what is that angle? Is theta 2. So look at x2 and look at x1. x1 is this one here. They are rotated. They are rotated about z1 by a amount theta 2. Yeah? So does the first statement make sense? Yeah? Does that mathematically make sense? Yeah? Okay. Now the second transformation is now here we have the translation of axes x2 and x1 along z. So we see that x2 and x1 are on the same plane, but we could translate them by the amount d along z. They are not translated here, so d is 0. But if they were translated, then the second frame would be coming out of the plane by a amount d. Yeah. The next one is zi was translated with respect to zi minus 1 along xi by a certain amount. What is that amount? Z1 and Z2 are translated along the line of x1 by a certain amount.
I think that's x2.
X2, yes, x2 along x2 by a certain amount, and you can see that is AI. Yeah, so this axis here was translated along that one by a amount AI. And finally, the axis Z were rotated about X by a certain amount. So these axes, both axes are coming out of the plane Right? And we did not rotate them across x, because that would mean rotating them that way, right? X, yeah, sorry, we're rotating up and down. Yeah, up and down. And they were not rotated because they're still parallel, so alpha is 0. Yeah?
Is there any relation to the fact that since we didn't move on Z, there's no angle, like there's no alpha? Or is that just...
No, that's independent. We did translate a rotate across Z by theta.
No, I meant there's no displacement across D.
No.
There was no D, so, but that has nothing to do with alpha.
No, those are 4 independent operations. Does it make sense? Yeah? Sort of? Okay. We good? Any questions? Let's do an example then. Will hopefully make more sense. Yeah.
Okay, it's not.
All right, so Miles answered his own question, so that's good. Any other questions? No. All right. Let's do an example here. Here we have a simple 3-link manipulator, and he wants to find all these parameters. We know the length of each of these links. The length is L1, L2, and L3, and you now want to find these parameters for all for our transformations. So here we have a table, links 1, 2, and 3, and then the parameters there. So what's the first step? Let's do the frame assignment. Where should we put the frames? Well, frame for link 1 goes at the end of link 1. Frame of link 2 goes at the end of link 2, and so on. So starting with link 1, here, how many axes we have here? We have 3. So here we have axis 1. Axis 1 is the axis about which link 1 rotates. Here we have axis 2, and here we have axis 3. So starting with link 1, we'll put frame 1 at the end of link 1. And you'll put frame Z1 along axis 2. Axis 2, exactly, axis 2. Because it's at the end of link 1. So here we have Z1 coming out of the page. Yeah? Where is Z2? Along axis 3. So this is Z2. No, yeah.
Are the little lines going through the joints just
Going.
enders of L, like the ones that are in the drawing? Is that just for L1?
These?
No. On the joints that are like.
These lines here?
Yeah.
Oh yeah, those just to specify the length.
Okay, so it would be wrong to put Z1 across.
Yeah, those lines are just arbitrary, just to show the length.
Does it matter which, like, what angle you put Z1 in? Like, is it always down? Well, I mean, I put it
No, it can go in the page or coming out, but it has to be along the axis. Now that we have Z1 and Z2, we can find X2. Where is X2? X2 must be normal to Z1 and Z2, so it will be on the plane formed by them, and it will be pointing towards the next link. So where should that go? So it goes like that, doesn't it? Yeah? So this is X2. And X2 goes along link 2. We can go all the way to the base here. Because our z-axis are coming out, we can assign our reference z here, z0, the base of the robot. We're going to be measuring everything with respect to that. And now that we have Z0 and Z1, we can find X1. Where is X1?
Along the link.
Along link 1. Link 1, right? Because it has to be parallel to Z1, orthogonal to Z1 and Z0. Go parallel on the plane formed by that. So it is like that. Next one. So our X1s are all going that way, so let's put our X0 here. And then we have a last frame to assign at the tip. We can simply translate now the frame 2 to the tip there. This would be Z3. And you have X3 following the same convention. Where are the Y's? Oh, we noticed something in our definition. We never used Y. We didn't even mention Y. We're only using X and Z. We don't need Y's. Right? We could omit them from here because we don't use them. But where would they go? Cross product. So the first one here, if X0 is coming out of the plane, Z0 is coming out of the screen, and Z is going that way, Y goes up. So Z1, Y1 goes here, Y2 goes there, and Y3, let me do it this way, goes up. Like that. Yep.
These Revolute joints are constrained to a plane.
Oh, yes.
If you had a ball joint that was like go up a plane, you just like choose that arbitrarily then?
Yes, we'll see that. Well, we have, yes and no. We have to define two axes, two independent axes, one for the rotation one way, the other one for the rotation the other way. And as soon as you define those axes, then you know where the Z are. We'll see that in the next lecture. Okay. Are we good with the frame assignment? All right. So we have now to define all translations and rotations. This is a planar manipulator. So we can first think about defining the way the Z-axis are rotated with respect to the previous one, with respect about X. Sorry, the other way. Excuse me, just to make things more confusing. How the X-axis are rotated about Z. Right, that's our theta. Where are they? We have 3 thetas here, one for each of the axes. Theta 1 is at axis 1. Theta 2 is at axis 2. Theta 3 is there. And what is theta representing again? The rotation between Z axis of 2 consecutive frames about X axis about Z. Yeah? Now we are ready to do the table there. Let's start at link 1. Let's do theta 1. Theta 1 is telling us how frame 1 is rotated with respect to frame 0. More specifically, how axis x1 is rotated with respect to x0 about z0. What's that amount? Is x0 with respect x1 with respect to x0 about theta 0 is theta 1. Right, we have theta 0 going this way, theta 1 is going slightly up. So it was rotated by a certain amount around that axis coming out around z0 by theta 1. What is d1? What is d1? What's the definition of d again? Let's look at the notes. What's d?
Translation across z.
translation, I have to look at my notes too. Translation across Z between x-axis. Yeah.
Is it sine
Hmm?
Would it be sine
No, let's look at that again. So D is the translation of axes x2, x1, and x0 along Z.
Cos theta 1.
Hold on. Along Z. Translation along Z. There is no translation. They are on the same plane. Yeah? So Z is coming out this way. We have frame 1 here, x0 here, and they have x1 there. They are on the same plane. They are not translated out of the plane. That's what D means. Right? If D was non-zero, then the second frame here would be coming out of the plane. So there's no translation along Z. Hence, D1 is 0.
Yeah, not even for y theta, when it goes theta 1.
Yeah, we'll get that.
Not even displacement in the y direction.
Right. Well, displacement in the Z. Let's do AI first. Let's do AI. So what is AI?
Translation across X.
It is the translation of Z-axis along X. So the translation of Z1 with respect to Z0 along X1. How much was that? So Z1 was clearly translated because these are not coincident anymore. They were translated along this frame with following X1 by how much? L1. By L1. Let's do that one more time. We have X0 coming here, right? And you have Z0 coming here. You have Z1 coming there. So they are clearly translated in space. Right? They are translated along this line here, which is the line of X1. How convenient is that?
So we need to take the magnitude of the.
This is the size of the link. And that's L1. And then the last one is alpha 1. And alpha 1 is now the rotation of the Z-axis about X. The rotation of the Z-axis about X. Are they rotated? No, they're still both coming out of the plane. If we were to rotate them about X, then we would be going up and down like that. They are both coming out. So what's theta? What's alpha I? 0.
Here, can I just distinguish the di equals to alpha I?
Di
Equals to alpha I.
why they are? Because
Still along the same
they're on the same plane. So these are you should treat each of these operations independently. There's no connection between them. Right? They are completely independent operations. Let's analyze them one by one. Let's do link 2. Now that you did link 1, you know how to do link 2. Link 2 is just now the end of link 2 here with respect to that. It's the same as before, isn't it? Because it is still on the same plane. The only thing that it changes is the translation and the angle along the translation along x2 and the angle around z1. What's the angle now between x2 and x1 about z1? Theta 2. What's the translation of the x-axis along z? Which is the translation along z of x2 with respect to x1. Still 0. Right? What is the translation of z2 with respect to z1 across x2? L2. And once again, both z's are coming out of the plane. Their translation around x is still 0. And what's the last line? Well, the last line is the frame of the tip there. So it's simply theta 3, 0, L3, and 0. And notice here that because this is a prismatic, a Revolute joint, the variables that make one frame change with respect to the previous one is the angle of rotation. If these were translational or prismatic joints, what would change? Either D or A, depending on how.
It would be L1 plus
Well, it depends on how they translate. Yeah, it would be D1 plus the extension of that frame, that element. Any questions here before we move on?
So for this one, it's almost kind of like the triangular swing. So in this case, the GI and AI probably should always be 0 because it cannot like this direction.
Yeah, in this case, yes, but there will be cases where it's not. All right, so what do we do with all this? Well, now we can calculate the orientation of the third frame with respect to the first frame. How do we do that? We simply multiply the rotation matrix of frame 3 with respect to frame 2 with respect to frame 1 with respect to frame 0. Multiply everything in cascade. And the result of that operation is a new transformation matrix, a new homogeneous transformation. That is still a 4x4, that it has in it a rotation matrix and a translation. What's the rotation matrix? Is the orientation of the last frame on the base frame. What is the translation? Is the Cartesian position of the robot's tip on the base frame. Yeah? So for this robot here, we had 3 frames, n equals to 3. So the result would be t from 3 to 0 equals to, when I is 1, we have t from 1 to 0 times t from 2 to 1 times t from 3 to 2. And now we multiply everybody there, and the job is done. How do we do that again? Well, now we look at our table, and for every transformation for I equals to 1, we go back here, we gather the parameters of line 1, input that into this matrix, and then we have transformation 1 to 0. Then you go to the next line, take the parameters there, input here, we have transformation from 2 to 1, and so on. And you multiply everything in the correct sequence, and then we have the final rotation and translation. Now, is it clear now that the result of this operation is a 4x4 matrix, and the vector there, px, py, and pz, is the position of the end effector of the robot with respect to the base of the robot? Does that make sense? Now you see the utility of all these stuff that we've been doing in the last 2 lectures. And what are those R1, R2, and Matlab? That's the orientation of the frame attached to the tip of the robot with respect to the base of the robot.
So, just a quick question. So the P would represent the link, the very first link.
P represents
the end tip of the very first link.
the P is, sorry, 1 second. P is right here.
Oh, okay.
All right, so P is a vector, and that's the vector.
Point of the whole.
Yes, and the end effector of the robot. My drawings keep getting worse and worse. Okay. Yeah.
Is the P 0 enough? It's the origin of the P, or it's the T?
This is the tip expressed in frame 0.
Oh,
You would have 3 P
we only have, well, we could have 3 P's, one for the end of each link, right? But when you go all the way to the end, then that's the position at the end. Okay. Now, if you want to know the orientation, the Euler angles, we can simply take the resulting transformation and then use the calculations we saw in the last lecture to find the actual orientation, the resulting orientation, the resulting 3 angles that will describe now the orientation of the tip with respect to the base. So let's move on. So you have 2 types of joints, as we saw in the last, or links as we saw in the last lecture. For revolute joints, the variable that it changes is the angle between them. So that's the angle, the twist around Z. Everything else is fixed. Doesn't mean 0, it means fixed. They don't change as the robot operates. For prismatic joints, such as these ones now that are translating, well, then you can clearly see that if a translation occurs, then the angle is now fixed, but the translation D is the one that it will change during operation. Okay? All right, so this is the summary, and that's all we need to know. How simple is it? That couldn't be. That's all that. All those 4 lines there. I made a prediction. I told Alec that I thought after this lecture we'd see a few people dropping out. But I'll see. It's not that hard, is it? Just take some practice. It's not that. And you know what? When you get a robot arm, all this is done. You are given these DH parameters. So you don't need to worry about assigning all this stuff. Just what I wanted to get from this is how to use it. So that's the final summary. And this is called the Denavit Hartenberg convention, the DH parameters of the robot manipulator. Anytime you buy a robot manipulator and you work with one, you have to know these DH parameters. And basically that's the collection of all these transformations for as many joints as we want, as we have, so you'll be able to calculate position of one to another. So that's all we need to know. Okay, let's do another example. So example 2. Let's try to find these parameters for this manipulator here. What you have there is a bit different. We have a system with how many joints? 2 joints and 1 translation. Right, so these joint here, this link moves like that, this link moves like that, and that one can extend and contract by the amount D. D is movable. So 3 degrees of freedom. It's still a planar manipulator because it's constrained to the same plane. So here is data redrawn. Let's now try to assign the frames to it. How do we start? What's the first step? Let's find the axis. First, let's go 1 step back. Let's find the axis. So this is axis 1. That's number 2. What's the third one? Third one is that one goes along D. That comes up and down in this particular case. It's a bit of a stretch to call that an axis, but that direction.
But that one also you have to represent in a 3D, or
no, this one is just coming out, going
so
up and down.
Just the new y-axis.
Yes.
Or, yeah.
Yeah,
New
it's
y-axis.
going up and down. So with A1 and A2, we can define our Zs. How many frames do we need to fully describe this? We need 1 on the base. We need 1 for the tip here. And another one for the translation. Okay, so let's start with link 1 there. So this is link 1. We can place Z1 over here. We can place Z0 over there. If you know Z1 and Z0, where is X1? It is along this plane, so it's got to be that one. So that is X1. So then we can call this one X1 as well. When you know X1 and Z1, then Y goes, cross product goes up. So this is Y1, and this is Y0. Okay, so here is where it's going to get a bit tricky. What's the next frame we need? We need 2 more frames. Right? Because all we have right now is the description of this point here. Well, what we want to know now is the description of that frame going up and down, and also the rotation of that frame. So we can split this into 2 separate operations. One operation that now gives the rotation of the second arm, and a third operation that it gives now the translation of the extendable part. So is it clear we need 2 more? If I want to split this into 2 degrees of freedom. Now where do I place them? Well, one goes at the tip, right? Because that's eventually what we want. One goes at the tip. So if one goes at the tip, where should we place Z3? Z3 is the last one at the tip. Where should Z go? Along the actuation axis. So it goes up. So this is Z3. And then the other 2 are either X or Y. We'll see that later because we can't yet define where X3 is because we need to know where Z2 is before we attend to that. Where is Z2? Let's put it this way. Where is the next frame?
Right before the extending.
We could place it anywhere. Anywhere along that line. You can put it just at the end where it extends there. And then you can say that the length that extends is D. Or we can take that frame and put it back here. And say that the length that extends is L2 plus D. It's the same. So it's up to us to put it whenever we want, so long as it goes along that line. So to make things simple, let's put the second frame back here. Coincident with frame 1, with one difference, it is rotated with respect to, it rotates with respect to that frame. Does that make sense?
So Z2 is like the same spot as Z1 or is it in the spot as Y?
Good question. Where should Z2 go? Z2 should go where Y1 is, pointing along the next axis. So this is Y1 and also Z2. Where, yeah.
Can you explain why it's in the C spot?
Because now we are dealing with the next frame will be rotated and also translated. So this frame here is basically it is putting it has the ability to would have the ability to translate. We're changing now the actuation axis from a rotation to a translation. Right? So instead of going around here, it goes along the actuation axis of next link. Where is x2? Well, x2, the only solution we have so that is perpendicular to z1 and z2 is there. And then the only spot left for y2 is here. Yeah.
In this way, it just x2 is not along the opposite position of x1.
x2 is not.
It's in the opposite direction of the x1 because if we rotate it like this way, it is going to the other side.
We rotate it like that. All right, so sorry, I'm not sure if I understand.
So right now it's like x, y, z, right? Then your z goes out like this way,
Mhm.
and then it is at I think
No, you use that first.
Yeah, we do z, then y, and then x. Z going up, then x, and then y. So y would be coming z. Sorry, I'm confused myself now. Z goes up, x goes that way. So y2 would be going back in the plane. In the plane, yeah. Z2 would be going back like that. Y2, sorry. The last frame is frame 3. Now for frame 3, you can simply translate the frame we have up because we know that it's simply a translation between them. So you can simply keep everything along the same direction like that. Y is not necessarily important, even though it's going in the plane. Now let's complete the table here. For frame 1,
sorry.
yeah.
So for the y2 is going inside, but y3 go outside.
No, then the y also goes inside. Let's forget about the y's because they don't add anything to our discussion.
Yeah, can we just define it as minus y3?
Yeah, or minus y3. Yeah. Okay. Why is this not updating? Okay, let's do the table now. For link 1, we are dealing with frame 1 with respect to frame 2. So what are the parameters there? What is IA? What is IA again? Is the translation of the Z along X. The translation of the Z or Z1 and Z0 with respect to X1 is the length of that link, right? So let's call that L1, so that is L1. Then alpha 1 is the rotation of z-axis around y. Did the z-axis rotate? No, they're still pointing out of the frame, so it's 0. What is di? D again represents the rotation of the the translation of the x-axis with respect to z. So the one of the x-axis would be coming out of the plane. Did that occur? No. All right, still 0. And then the last one is the translation of x1 with respect to x0 around theta 0. That is theta 1. Same as before, right? Nothing new. Now let's look at link 2. Now link 2, we are looking at this 2 here. Is there any translation between them? No, so we can right away say that which parameters are 0. A2 and D2 are 0 because the frames are coincident. So this one and that one are 0. Now let's look at the other ones here. What is alpha I? Alpha I is the rotation of the z-axis with respect to x2. So z was pointing like that and then went up across x. You see, if it went up, it went clockwise or counterclockwise? Clockwise. Right? Clockwise. Clockwise. Or counterclockwise. Is clockwise. So that is negative 90 degrees. Is x1 and x2, can x1 and x2 rotate about z1? Can x1 and x2 rotate about z1? They can. They can, because that's exactly the angle here. Now they turn out to be aligned. Theta is 0. But if theta wasn't 0, then x1 and x2 would rotate with respect to one another along the common z-axis z1. So what's theta 2? Oh, sorry, what's theta 2? Is theta 2? What a stupid question. And now let's go to the next one. Let's look at the angles. Next one is the third frame with respect to the second frame. They are not rotated, are they? At all. They cannot rotate with respect to one another. They can only translate. So we can say that theta 3 and alpha 3 are both 0. What is alpha? What is AI now? AI is the translation of the z-axis with respect to x. Is the z-axis, z3, translated along x? No. So that is 0. What's D? D is the translation of the x-axis along z. Can x3 translate with respect to x2 along z? Yes, it can. By D plus L2, and L2 is that distance. So you see, the trick is to find the correct placement for the joints, the frames. Once that is established, then everything else is just a matter of following the chart. Okay, any questions? We'll continue this in the next lecture, and then next lecture, bring your laptop or a tablet with Matlab. We'll code this to probably make more sense.
Did redrawing it affect like the frame convention or anything? It does.
It made it easier. It didn't affect it. It made it easier. So I kind of cheated a little bit because I already put it in a convenient position. Yeah.
I'm still not sure why it's the cap.
Yeah,
Clockwise.
why is it clockwise?
Okay, let's fix that. So we had Z1 coming like that, right? So Z1's coming like that, and then Z goes up, and you're measuring that across X1, right? Across X1. Yeah, so if it goes across X1, it is rotating back. It's rotating across X1 this way, because it was like that and it goes up.
It's like this.
Oh.
So
Right? Yeah. Back. All right, let's do one more exercise. And then next lecture we'll come back to this because this is it's complicated. I understand that. I get confused myself sometimes, so I don't expect you to get it all at once. So here we have the same manipulator. We just found all the parameters for this one. Now let's assume that all the A's here are 10. We have theta 1, theta 2, and theta 3. And they're going to assign specific values of 90, minus 90, and minus 90 for theta 1, 2, and 3. We want to find the in the factor position and orientation for those values. So what do we do? What do we do here? We have them here, we found them before, just assign numerical values for them. So we need to find the 3 transformation matrices. How do we do that? We simply take the table and there's an input here. For the first transformation, that would be when I is 1. And that transformation goes from frame 1 to frame 0. How do we get that now? Well, we look at line 1. They're going to input the numerical values here and see what comes out. So what comes out there? Let's do cosine of this is 90, this is negative 90, and this is also negative 90. Cosine of 90 is 0. And the bottom one sine of 90 is 1, 0, 0, and so on. You can complete the whole table. Yeah? So you know how to do that? Is that clear? So can I just give you the numerical values? Or we can spend 3 hours filling that up. So here are the numerical values. Is it clear how we got them? Yeah? All right. Now let's see what this means. So the first one, let's look at the first one there. The first one is saying we had a manipulator. The manipulator had 3 links, like that. Let's look at the first link only, because you're only dealing with the first transformation. Where are the frames here? This is Z0, X0, and Y0. And this is Z1, X1, Y1. This is now theta 1. And theta 1 was 90 degrees. So if theta 1 is 90 degrees, how does the robot look like after a rotation of 90 degrees? It simply goes up. Where are the frames now? Oh, frame 0 doesn't move. Where is frame 1? Well, X1, Z1 doesn't move. X1 now goes up. Up. Yeah. So Z1 comes out of the plane, X1 goes up, and Z1 goes, right? You're just taking this and rotating it up. Now let's look at the result of your rotation matrix and see if that rotation matrix agrees with what we see here. What is the height there? The height here is 10. That's the length that was given before. Yeah? Now look at the rotation matrix. Where is the final position of frame? So that rotation matrix gives the position of this frame with respect to that. Does that make sense? It is telling us that the position of frame 2, frame 1, is at 0, 10, 0. It means that in frame 0, the x-coordinate of the tip is 0, which makes sense because it is a line. It is shifted 10 up and 0 along Z. So it makes sense. Now let's look at the orientation. What do we see from your orientation part? Let's look at this one here. We have 0, 1, 0. What is that again? Is the coordinate or the component of x1 in x0, y0, z0. So this is telling us that the component of x1 in x0 is 0. Is that the case? Yes, because they are orthogonal. It is telling us that the component of x1 in y0 is 1. Does that make sense? It is, because now they are parallel. And then the last says that now the component of x1 in z0 is 0. Does that make sense? It does, because they are orthogonal again. Right? Yeah? Let's look at the second column there. Second column says that the component of x1 the component of y1 in x0 is -1. Is that correct? Yeah. All right, the component of x1, y1 in x0 is -1. So you see now what this rotation matrix is telling us? The orientation and position of the end effector. Does that make more sense? Yeah? Okay, so now let's do the final transformation here. If we do all three joints, how would the robot look like? We are doing theta 1, 90, theta 2, -90, theta 3, -90. So how does the robot look like with all those rotations? It would be up. Then the second one, instead of going up, is going -9, so it goes like this. And then the third one is also going downwards. Where are our frames? And that's the biggest question. Well, Z1 is here, Z0. We have X0 and Y0. What is the frame at the end effector?
It's just a shift. The original of the x, and then the shift is 10.
Z was pointing, coming out, right? X was coming out. So X is now going down. Yeah? Let's look back here. Where did I have it? Did I draw it somewhere? So if you look at this one, you have three of these components just extended, right? So the last one is this, but now pointing downwards. So we have Z doesn't move, Z3. Z3 comes out, X3 goes downwards, and Y3 points that way. Does that make sense?
I thought Z3 was a prismatic joint, isn't it?
No, these are all Revolute.
Oh.
All Revolute.
Oh.
So Y was pointing up here, now it's pointing, when that points downwards, then Y points that way. X was pointing that way, now when it points down, everything points down, and X and Z is coming out, right? So let me just rush here to finish this on time. How do we calculate the final rotation matrix? Well, the final rotation matrix is 3 to 0, which is T exactly 1 to 0, 2 to 1, and 3 to 2. And the result of this, I'll give it to you here, is 0, -1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 10, 0, 0, 1. Now, does that make sense? Let's analyze this. What's the length of each of these is 10, right? Each of these is 10. That's 10, that's 10, that's 10. Without looking at the result, what is the coordinates of the tip of the robot with respect to the base?
10.
X is 10. Y is 0 because it's aligned here with the origin. And the Z is also 0 because it's in the same plane. Now look at the transformation. Here we are.
And we define x0 as the one pointing that way after
Yeah.
knowing the endpoint.
Yes, well, this was the first step we did.
But why would we, because if we were doing it following the steps, wouldn't we?
If you're doing following the steps, it's the same exercise that before. The entire robot would be aligned in a line like that. So all the axes will be pointing towards the next joint.
But so x0 is pointing towards the last point.
Towards this one when theta is 0. Because it's now 90 degrees. So when the robot, when all thetas are 0, this robot is aligned like that. So x always points to the next one. So let's look at the rotation matrix. Is the rotation matrix correct? Rotation matrix is telling us that the coordinate of x3 on frame 0 is here. 0 on x makes sense, they are orthogonal. -1 on y, how y goes up, they are going down. And 0 for z. What's y? Y is aligned with x3, x0, excuse me, where 3 is aligned. So you see the component of y3 in y0 is 1. The component of y3 in y0 is 0 because they are orthogonal. And z, and y on z is also 0 because they are orthogonal. And then the last one here is simply the z-axis. This is telling us that the y-axis are aligned. Right? Right? And most importantly, in these elements here, we see the vector that locates now this frame with respect to that frame. Does that make a little more sense?